Hello everyone. Let me start with a simple puzzle. Have you ever folded a paper triangle with two equal sides along its altitude? You'll notice the two halves overlap perfectly. That's the beauty of an isosceles triangle. By definition, an isosceles triangle is one in which at least two sides are equal. Now here's the property. If in triangle ABC, side AB equals side AC, then the angles opposite to them, namely angle B and angle C, are also equal. This is formally stated as Theorem 7.2, angles opposite to equal sides of an isosceles triangle are equal. And the proof of this rests on congruence, specifically the side-angle-side rule. Let's dive into a beautiful property of isosceles triangles. Equal sides give rise to equal angles. Suppose we have triangle ABC with side AB equal to side AC. To prove the base angles equal, we draw the angle bisector AD meeting side BC at point D. Now look closely at the two smaller triangles ABD and ACD. In these, side AB equals side AC, angle BAD equals angle CAD because AD is the bisector and side AD is common. By the side-angle-side or SAS rule, triangle ABD is congruent to triangle ACD. And if these two are congruent, it directly follows that angle B equals angle C. So we've proven that if two sides of a triangle are equal, then the angles opposite to them are also equal. Quick insight, this neat property comes straight from SAS congruence. It's the key to establishing equality of base angles in isosceles triangles. That's the power of logical reasoning in geometry. Hello everyone. Here's something truly fascinating. If equal sides give equal angles in a triangle, then the reverse must also be true. Let's explore this converse idea. Theorem 7.3 tells us if two angles of a triangle are equal, then the sides opposite to those angles must also be equal. Take a look at triangle ABC, where angle B equals angle C, each being 50 degrees. Now, by drawing a suitable construction such as the bisector from A to D, we can compare the smaller triangles. Using the angle-side-angle congruence rule, we find that side AB must equal side AC. This means that equal angles force the triangle to be isosceles. It's not just a coincidence, it's a guaranteed result. So here's the quick insight. Whenever you spot two equal angles in a triangle, you can be absolutely sure that the opposite sides are also equal. Equal angles always guarantee equal sides. That's the elegance of geometry. One equality leads naturally to another. Hello everyone. Let's now flip the idea we studied earlier. We know that equal sides give equal angles. But what if we start with equal angles? Can we prove the sides opposite to them are also equal? The answer is yes, and here's how. We are given triangle ABC where angle B equals angle C. To prove that side AB equals side AC, let's use a simple construction. Draw the angle bisector of angle A and let it meet side BC at point D. Now, let's carefully observe the two smaller triangles, triangle ABD and triangle ACD. In both, angle BAD equals angle CAD because AD is the angle bisector. Side AD is common to both triangles. And we were already given that angle B equals angle C. That means, by the angle-side-angle congruence rule, triangle ABD is congruent to triangle ACD. From congruence, we can directly say that side AB equals side AC. So we've proved the statement, equal angles force equal opposite sides. And here's the quick insight. The ASA congruence rule is the key bridge that establishes equality of sides whenever angles are equal. Geometry never fails to show us this beautiful balance. Hello students. Let's take another interesting case of isosceles triangles. Did you know that in such triangles, the angle bisector from the vertex also becomes perpendicular to the base? Let's prove that step by step. We are working with triangle ABC. Here, we draw the bisector of angle A and it meets the base BC at point D, making a right angle. Now, look at the two triangles formed, triangle ABD and triangle ACD. In these, angle BAD equals angle CAD because AD is the bisector. Side AD is common to both triangles. And we also have angle ADB equal to angle ADC, each equal to 90 degrees. So by the angle-side angle congruence rule, triangle ABD is congruent to triangle ACD. From this congruence, we can conclude that side AB equals side AC. That means triangle ABC is isosceles. And here's the quick insight. Whenever you draw a perpendicular bisector from the vertex of a triangle, it directly proves the isosceles property. Geometry once again shows its perfect symmetry. Hello everyone. Let's explore how congruence not only matches shapes but also helps us deduce new equalities between sides and angles. This is where CPCT, corresponding parts of congruent triangles, becomes a powerful tool. We begin with triangle ABC, where AB equals AC. A construction is done so that AB equals AD and AC equals AE with angle BAD equal to angle EAC. Our target here is to prove that side BC equals side DE. Now, let's focus on triangles BAD and EAC. We can clearly see that AB equals AD, AC equals AE, and angle BAD equals angle EAC. So by the side angle side congruence rule, triangle BAD is congruent to triangle EAC. Once we have congruence, CPCT tells us that corresponding sides are equal. That gives us the key result, side BC equals side DE. The quick insight is simple yet powerful. CPCT acts like a bridge. Once triangles are congruent, CPCT links different sides and angles, helping us discover new equalities that weren't obvious before. Let's wrap up everything we've learned. In an isosceles triangle, equal sides imply equal opposite angles. That's Theorem 7.2. Conversely, equal angles imply equal opposite sides. That's Theorem 7.3. Proofs rely on congruence rules, side angle side for one direction, angle side angle for the other. Applications include perpendicular bisectors and symmetry reasoning. And most importantly, once congruence is established, corresponding parts of congruent triangles allow us to deduce further equalities. So, the isosceles triangle is a perfect example of balance between sides and angles. In the next video, we'll take this a step further and explore inequalities in a triangle, understanding why some sides must always be longer than others.